Good morning, good afternoon, good evening, whichever is applicable to you. Welcome to our virtual lecture today. I want to start chapter 2, and as usual, there are two parts, part A and part B. Make sure to come back and watch part B once you're done with part A. I will share my screen. You will have the whiteboard on the left side of your right side of your screen, and the PowerPoint slide will be on the left side of your screen. I'll be showing you a calculation on the whiteboard, and it's good to share my screen. And part A for a lecture will cover section 2.1 through section 2.6. In part A, we will look at the Brownian motion and how the atoms were conformed. Section 2.2, early ideas that led to understanding of the building blocks of matter, which we defined earlier on in chapter 1. As matter is anything that has mass and occupies space. Remember that. In section 2.3, we will look at the modern atomic theory and the laws that led to it. There are three laws which I know you are familiar with: the law of mass conservation. May have covered that in Introduction to Chemistry. We will look at the law of multiple proportion and law of definite composition. In section 2.4, we will look at how the electrons was discovered, the structure of an atom. In section 2.5, and lastly in part A, we'll talk about the subatomic particles, that is the protons, neutrons, and electrons. Let's see, in part B, this is where I'll talk about the finding pattern of an atom, atomic mass, and the molar mass. Let's see, part A. If you cut a piece of graphite, how far can you go? The answer to that is, if you cut a piece of graphite from the tip of your pencil into small pieces, you could go, will you go on forever, or there will be a definite dead end? The answer to that is there is a dead end, which we call the atom. And the atom is derived from the Greek term atomos, all right, which means indestructible, indivisible part of matter. This is the answer to the question that could you divide it forever? No, you will divide the tip of your pencil to an end, which will lead you to the atom. An atom is defined as the smallest indestructible, indivisible matter, part of matter. And how did we end up there? There are several experiments which led to the development of an atom, which I'm going to talk about shortly. But cutting the graphite from a pencil tip into small pieces, you can go as far as small individual we call carbon atoms. Remember, the graphite is made up of carbon. Now, if you cut that, you'll end up with what I just defined, atom, which means atomos in Greek. Atomos means indivisible, indestructible. Maybe you need to write down that you can subdivide the carbon atom in small pieces. This is what you need to know. And moving forward, you need to know that those terms, which are highlighted either in the text, in the PowerPoint slide, you need to commit to your memory. So remember, if you cut a graphite in the tip of the pencil, you'll end up with an atom, which is the dead end. Atoms compose all ordinary matter. So if you can think of anything, they are made up of atoms. If you want to understand matter, definitely you will need to understand the atoms which makes up them. How did we end up with the atom? It started with the Brownian motion experiment, and Brownian is a name of an individual, he performed an experiment which led to what we call the Brownian motion. He was a Scottish, and in 1829, he developed, he developed what we call the Brownian motion. And in this experiment, when you observe the tip, or when you observe water molecule through his microscope, he saw some movement. He noticed that the particles were in constant motion, and he could not understand why or what caused them to move. It's because of the water molecule. Later on, it was established by Albert Einstein in 1905 that the movement of pollen, which he noticed, was as a result of the water molecule moving. And in that, the water molecule moved because of the thermal energy, and by bombarding the pollen, Brownian noticed that the movement of the particles was as a result of those water molecules. He thought at first probably it had to do with the living part of the plant, but even dead plants could be observed under the microscope, showing the same behavior. What was causing them, as I explained, had to do with the movement of water molecule as a result of thermal energy in them. You can read more about the Brownian motion. And because of that, Albert Einstein explained that water is made up of atoms, and the atom possesses what we call thermal energy, and the thermal energy made the water molecule move around, and when they move around, they were bombarding onto the pollen in water, and what really caused the movement of pollen in Brownian motion. Now, I don't want to spend more time on section 2.1, Brownian motion. Please, that's just the beginning of looking at the atoms. We're gonna come back again to the elements. Having said that, remember the meaning of the word atom is indestructible, indivisible part of matter. Now, these atoms makes up in chapter 2, we will look at the elements. And what are elements? These are the building blocks of what? Building blocks of matter. And you have seen on the periodic table of elements, maybe I can show you what's the periodic table. These are elements on the periodic table. So for that matter, understand what the atom is, and atoms make up element on the periodic table. I know you have covered this. To give you a heads up, please learn memorizing the chemical symbols for element, the first 50, and the most common one on the transition metals. You should be able to break the periodic table into main group element. We're going to talk about that, but this is the periodic table of elements, which we will look in details in chapter 2. So back to our PowerPoint slides. There are ideas which led to early development of the atom. Starting off with is the contribution by Lotus, all right, and Democritus. Both of them, they were Greek philosophers. Recall early times philosophers, they were so powerful, they had large followings. And these two gentlemen, they invented the atomic theory, okay? That is way back before Jesus Christ was born, that means by BC. They were the first to propose that matter was composed of small, indestructible particles, and these particles are what we call atoms. I've highlighted their names so that you draw the parallel. By the end of chapter 2 and even moving forward, you'll be given different personalities, different scientists who are credited for different contribution towards development of the periodic table, for example, and you should know them. So make your own notes on who did what. So the first one was Democritus, and in fact, Democritus proposed that or wrote that nothing exists except atoms and empty space. Everything else is opinion. These were their proposal that different kinds of atom existed in each or in different shapes and sizes. They move randomly through empty space. This statement here is just statement of these two scientists, and what we know is you're just looking at the atoms. Now, two other scientists, two other Greek philosophers, in ancient Greek, Plato and Aristotle, they did not embrace the atomic idea of Democritus, because with them, they believed that matter was continuous. What do I mean by continuous? They believe that there is no end. If you think of, let's say, if I have a piece of paper here, if I divide it into two like that, I'm dividing the paper into two. You may see I have two papers. I don't know if it's visible, but assuming that you can see that I have two pieces of paper, if I subdivide a paper again into two, or subdivide it again into two, the other gentlemen believe that there is a dead end, and dead end is what we call the atom. But Plato and Aristotle believed that matter was continuous. That means there was no dead end. And in this case, think of it that there were two schools of thought. One believed that there is no dead end if you subdivide matter, and the other believed that there is dead end. In this case, Aristotle and Plato believe that there is no dead end. Okay, we will see who is going to prevail. The two believe that different substances were composed of various proportions of fire, air, and water. These were just think of like their periodic table at that time, that anything on the earth is made up of either fire, air, and earth, and what? And H2O, that everything else was made out of these four substances. But seems like they were wrong. We'll see in details later on. As more questions were asked regarding matter, scientific method, which is a methodical way of doing science, were invented, all right, and it became the established way to learn about the physical world. Scientific approach, think of scientific method where you make observation, you come up with a hypothesis, make observation, do the experiment. That's what we call the scientific method, coming up with an hypothesis, testing the hypothesis, collecting the data, making the observation, drawing the conclusion. Remember, they were just speculating what matter was really made of. Now, in an English chemist, which you know, Dalton, from the Dalton's atomic theory in early 18th century, offered a convincing evidence that supported the early atomic ideas of the divinate, the dead end of matter, which we call the atom. He came up with a theory, all right? He didn't do any experiment, but remember there are about 5 postulates which he proposed. We're going to look at each one of them, all right? The theory, that's Dalton's atomic theory, that all matter is composed of atoms grew out of observation and laws. Remember, observation, experiment, theory, scientific law, and so forth. This is what he proposed. The 3 most important laws that led to the development and acceptance of atomic theory, which you need to know, is obviously, you know, the law of mass conservation, which states that matter cannot be created or destroyed. We'll talk about that. There is the law of definite proportion, and lastly, the law of multiple proportion. These are the most important laws you need to remember. Of course, they are not like the government laws. No, they are not like the civic laws. What I will expect you is dividing these laws and tagging to the scientist who invented them and what's all about. Let's start off with the first law, the law of mass conservation. The law of mass conservation is or was proposed by Antoine Lavoisier. Let's just call him just Antoine. And he proposed that the law of mass conservation says that in a chemical reaction, matter is neither created or destroyed. That is the law of mass conservation as proposed by Antoine. And basically what he was working on, he was burning a substance, weighing the substance before and weighing the product after, and he realized that there was no laws of mass. Weighing before or mass before and mass after should be the same. We call it law of mass conservation, and this holds until today. In a chemical reaction, so what happened in a chemical reaction when we mix reagent A and reagent B, chemical reaction occurs, but what happened is just taking of the chemical bonds and making of new chemical bond. We do not destroy the atoms. All what is happening in a chemical reaction is rearrangement of our atom. There is no net change in chemical reaction. The law is consistent, as the law of mass conservation is consistent with the idea that matter is composed of small, indestructible part of matter. This explains why, if you think of the mass of the reagent and the mass of the product, you got to look at the total mass before and total mass after. Mass of sodium and mass of chlorine before you react is 19.16. Mass of sodium chloride produced from the 2 reagents is exactly the same as the mass or the combined mass of the reagent. This is basically the law of mass conservation. You should always remember that. Yeah. Let's see, here is a conceptual question. These problems, the conceptual question, they are available in the lab, in the text. Please, when you get your text, I'm assuming you have your text, read, be using also those conceptual questions to study. But here is one of them. When a log completely burns in campfire, the mass of ash is much less than the mass of the log. What happens to the matter that composes the log? You have to think of, this is the law of mass conservation problem. Matter that compose the log react to form gases that are released into the atmosphere. The matter that compose the log is converted into energy. We talk about the energy. The matter that compose the log is still present in ashes, but as much lower mass. B and C are wrong. The most appropriate answer for this is that the reason why the mass of ash is less than the mass of the starting log is because part of the product or part of the products are gases which are converted into gas, and it will escape into the atmosphere. That's the correct answer. It is the law of mass conservation problem. Okay, matter cannot be created or destroyed. Don't think that because there is less mass of the law, then matter was destroyed during the process. It's only that gases were released into the atmosphere, which is part of, or which was part of the law. Still on law of mass conservation, the statement in a chemical reaction, matter can neither be created nor destroyed is called what? The law of conservation of mass, Dalton's atomic theory, the scientific method, the law of multiple proportion, the law of definite proportion. The correct answer for that is A. I need to write on my whiteboard. Correct answer for that is A. You need to know that it is A. The correct answer is the law of mass conservation. Law of mass conservation. Please use end of chapter problem to practice more on law of mass conservation. There are some calculation. Now, law of definite composition or law of definite proportion. This was proposed by Joseph Prost. You also need to know the name of the scientist who came up with it. And it states or it summarizes that all samples of a given compound, regardless of their source and how they were prepared, have the same proportion by constituents. So if we think of H2O, all right, whether it is sourced from Canada, Mexico, Australia, United States, these all have the same composition. Still gonna remain as H2O. It will never change. Similar with sodium chloride. No matter where we saw sodium chloride, it will still consist of one sodium and one chlorine. I'll commit to my memory using the word divinate. That means it's well defined, regardless of what, regardless of the source. The law of definite proportion is sometimes called the law of constant proportion. So in the exam, when you see the law of definite proportion, law of constant composition, it means the same thing. For example, the decomposition of H2O, we have 18.0 grams of H2O, all right, breaking down to oxygen and hydrogen. Look at the mass of oxygen, mass of hydrogen. The ratio of the two elements in the compound is a whole number ratio. This is a law of definite composition. Please be well-rounded so that when you are given a problem, such as this one, law of definite proportion, we just saw that mass ratio of nitrogen to hydrogen in ammonia is 4.7 to 1. That means if we have ammonia, Na3, and the ratio of what? Ratio of, let's say here, if I have in ammonia Na3, the ratio of nitrogen to hydrogen is 4. 4 ratio of nitrogen is 4.7 to 1, 4.7 to 1. This means if we have 10 grams of hydrogen, that means we'll have 47 grams of 47 grams of nitrogen. How many grams of N? N stand for nitrogen here. And using this constant proportion, I'll just multiply by 10 so that we have that as the ratio between the two. Now, for law of mass multiple proportion, if we use A and B, you see ratio is 1:1, 1:2, 1:3, and so forth. We're using here example of A and B forward for the two elements. Here using oxygen, carbon, we take the mass of oxygen and carbon in carbon dioxide. The ratio is 1:1.3. If we look at the other sample, if we take the two ratio for carbon dioxide and carbon monoxide and take the ratio of mass of 1 gram of carbon to 1 gram of carbon, all right, mass of oxygen to 1 gram of carbon in carbon dioxide, and mass of oxygen to 1 gram of carbon in carbon monoxide. Take the two ratio, we end up with our own ratio. This is the law of multiple proportion, and it's credited for John Dalton. It's credited for this. Let's see, John Dalton's atomic theory, he proposed that based on the three laws, someone came with the law of mass conservation, they proved it, they couldn't explain why. Law of definite composition, they couldn't explain what's going on. And the law of multiple proportion, those were, there were experimental evidences for all those laws. And remember in chapter 1, we talked about the law before, and an hypothesis is proven wrong. It got to be tested multiple times before it is elevated to a law. Now, Dalton now and the atomic theory is based on the three laws we discussed. You should know the three laws: law of mass conservation, law of definite composition, or law of constant composition, and law of multiple proportion. There are three laws which now John Dalton uses to propose the atomic theory. Dalton's atomic theory. He did not illustrate how the atom looked like, but he just came up with a proposal. Sometimes we call this John Dalton's postulate on atomic. And this is what he explained, that elements, which are the element on the periodic table, are composed of, each element is composed of tiny indestructible particles we call atom. That's what we know. That the reason why we don't see any change in mass during a chemical reaction is because we are not destroying what? We are not destroying atoms. Secondly, all atoms of a given element have the same mass and other properties that distinguishes them from other atoms of the element, all right? We'll see later on that number 2 is no longer valid because not all atoms of the same element have the same mass because of the isotope. We'll talk about the isotope later on. Atoms combine in simple hole ratio to form compound. This is true because if you think about sodium chloride, let's say sodium chloride, NCl, there is no way you see Na2Cl3, for example. This will not exist. They combine in simple whole number ratio, or H2O having a ratio of 1 to 0.5. This will not exist. Or when we have that like fraction, they must have a whole number ratio. Lastly, atoms of one element cannot change into atoms of another element. In a chemical reaction, atoms only change the way that they are bound together with other atoms. In other words, they just rearrange them. It's not that the sodium atoms will change to chlorine atoms and chlorine atoms will change to sodium atoms in the chemical reaction to form sodium chloride. It's just the way they bond that really matters in a chemical reaction. Here is a learning check. Dalton's atomic theory states that all elements have several isotopes. Matter is composed of small indestructible particles. The properties of matter are determined by the proportion, all right? Properties of atoms. Energy is neither created or destroyed during chemical reactions. An atom is predominantly empty. So here is testing if you know what constitutes Dalton's atomic theory. All elements have several isotopes. We didn't talk about that. Matter is composed of small indestructible particles. That's correct. That's correct. That's the correct answer for this question. Please make sure you read more on Dalton's atomic theory. B is one of the postulates, Dalton's atomic theory. There are 5 postulates, 5 assumptions, which makes up Dalton's atomic theory. Which statement best captures one of the differences between the law of definite proportion and law of multiple proportion? The law of definite proportions applies to 2 or more substances of the same compound, while the law of multiple proportion applies to 2 different compounds containing the same 2 elements. I don't think so. The law of definite proportion applies to 2 different compounds containing the same 2 elements, A and B, for example, while the law of multiple proportion applies to 2 or more samples of the same compound. None of the above. I think the correct answer is A. The law of definite proportion applies to 2 or more samples of the same compound, definite, while the law of multiple proportion applies to different compounds. So here, same compound, but here different compound, they may have different combination for that. Section 2.4, discovery of electron, J.J. Thomson. We'll see how the electrons were discovered. J.J. Thomson, his name is, let's see, full name is Joseph John Thomson. He was a Nobel laureate in physics, was from Britain, and he is credited with the discovery of electron. Please remember the name, the contribution he made in the development of the atomic theory. He was working with the cathode ray. I will post to YouTube on cathode ray experiment. And in his experiment, he constructed a partially evacuated glass tube called the cathode tube. Evacuated means it was a vacuum. There was no air in it. The most important thing is the outcome, what he observed. He found that a beam of particles called cathode travel from negatively charged electrode. There were 2 electrodes in A, B, all right, where B, in this case, anode, negatively charged. Remember, electrons are negatively charged. Let me just minimize this so you remember electrons are negatively charged. Get that? Negatively charged. So from his experiment, he was able to conclude that what the stream traveling from negative to positive, all right, cathode, anode, there is a stream. You see the stream of particles from negative to positive, which later on turns out to be electron. Thomson found out that the particles that compose the cathode have the following properties. They travel in a straight line. They have, all right, they are independent of the composition of the material from which they originate. They originated from the cathode, and remember, cathode is negatively charged. And all right, they carry a negative electrical charge, which we know electrons are negatively charged. We'll see later on that protons are positively charged and neutrons are neutral. What I expect you in this section is who discovered the electron. Sometimes you may see which year, may find out, and the negative, or rather the electrical charge of the particle. So in this case, electrons are negatively charged. And from classical physics, we know positive, negative to attract, positive, positive repel. And if you look at here, there is attraction between negative and positive charges. Once Thomson discovered the electrons, he proposed a model of an atom. Right now, remember those laws, how it led to the discovery of an atom. John is proposing now, J.J. Thomson proposed a model of an atom we call Plum-Bardeen model. Remember, there is a Plum-Bardeen model. The reason why I do have here one Plum-Bardeen model is because of different models of an atom. Let's say models, all right, of an atom. There is if you want to make your own notes, this is one, John Dalton atomic theory to Thomson model of an atom we call Plum-Bardeen model. 3 Ernest from New Zealand, Rutherford model. We'll see later on. This is called the nuclear model. 1, 2, 3, 4 here. And where we are currently in terms of the model is the quantum mechanical model of the atom. Quantum mechanical model of an atom. So these are the models of an atom. And for the first time, we are looking at the actual diagram of what the atom look like. Thomson used a sphere to represent an atom, of which his model proposed that it is just a sea of negatively charged particles. In this case, electrons are uniformly distributed within the spheres of positively charged. Remember, positively charged particles here are protons. So here, negative, or I'll say electrons, 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 electrons. And then there is also protons, 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 protons. This is the Plum-Bardeen model represented by the sphere. This model is popularly, or the most popular of the time, became known as the Plum-Bardeen model. I've seen in the question, or some question asking, who is credited for this model, Plum-Bardeen model? The correct answer is J.K. Thomson, if you see in an exam or a quiz. So here, we have looked at the Dalton's atomic theory, all right, and Thomson model of an atom, which is like a sphere like that. Now, let's move on to the Ernest Rutherford. What Ernest did was he performed an experiment using the J.K. Thomson and He had worked with radioactivity, alpha particles, which are positively charged. Here, Rutherford, NS. Rutherford, he worked with alpha particles, which are what? Positively charged. And what he was proposing is, if this is Thomson model of an atom, you expected the positive charges to cut through, all right? And he had an hypothesis that what will happen if I run through a very thin coil foil of coal with these alpha, which are positively charged particles. What will happen if I run that? His assumption was, if the source here, I want you to picture this as positively charged particles coming from the source, lead positively charged particles. And remember, in a nucleus, we have what? We have, or we didn't have, or he didn't have an idea of where the nucleus is, but he was thinking of the cold foil having same structure as Thomson model. He had an hypothesis of what will happen if we bombard the tin foil. You'll watch on the YouTube how the experiment went. Rutherford experiment gave an expected result than what he anticipated. The majority of particles, which in this case the positive charge, pass through direct through the foil, but some particles came back, or bounced back. 1 in 20,000 bounced back. Rutherford created a new model. We call this nuclear model. Here is the what he predicted, that the alpha particles will go through the model. It's in this case the J.J. Thomson model. Electrons, these are alpha particles, but this is the actual. Majority went through, some bounced back, all right? But majority did what? Went through, some bounced back, some just deflected a little bit. This led to what we call nuclear model of an atom. He concluded that matter must not be as uniform as it appears. It must contain large region of empty space dotted with a small, very dense region we call the nucleus. And in the nucleus, we have protons and what? Protons and neutrons. In the nucleus, we have protons and neutrons. So we have revolutionized the model of an atom to be just a sphere with protons and neutrons in the nucleus. We call this nucleus. It's a dense region within an atom, and outside we get just electrons. Building on this idea, he proposed the nuclear theory. This is what we call the nuclear model of an atom. Nuclear model atom. Yeah, so the change has changed, nucleus. The nuclear theory proposed that the three basic parts of an atom is the nucleus, which is what I've indicated in there. And most of the volume of an atom is just an empty space throughout which tiny negatively charged electrons are dispersed. So here are the electrons. The electrons are dispersed. I'm just going to have electrons, around with a negative charge. This is E for electrons with a subscript negative showing the negative charge. Thirdly, there are as many negative charged particles outside the nucleus as there are possibly charged particles in the proton. In other words, the number. All right. Remember these four neutral atom, number of electrons equals the number of protons. Later on, we look at the ions. We do not have the same number of protons or electrons. When they lose electrons, when a neutral atom loses electron or electrons, the number of protons and number of electrons are no longer the same. So these are the conclusions from Rutherford's coil experiment. Remember, for a neutral atom, the number of electrons equals number of protons. Here is a learning check problem on Rutherford coil experiment. The coil experiment performed in Rutherford's lab confirmed the Plum-Bardet model, led to the discovery of atomic nucleus. Sounds good. Was the basis for Thomson model of an atom? Nope. Thomson came much later. I mean, earlier on, before Thomson. Utilized the deflection of beta particles by coil? No, he did not utilize that. He utilized the positively charged particles and proved the law of multiple proportion. The correct answer here is led to the discovery of the nucleus. Led to the discovery of the nucleus. That's the correct answer for that. Now, the neutrons. So we have talked about the electrons, the nucleus, but it turns out that when scientists look the masses of those elements, they notice something that, it keeps on increasing, and it had to do with the number of neutrons. We do not carry what? They do not carry any electrical charges. They do not carry electrical charges. Although Rutherford's model was highly successful, scientists realized it was incomplete. Why? Because the masses of elements increase because of existence of neutrons in the nucleus, which was not accounted in the masses of those elements. So here is the discovery of the neutron. Remember, Thomson discovered the electron. Now, James Chadwick discovered electron. He was a Briton from Britain. He proved the existence of a neutron, and basically discovered the neutron, which have no charge. So you see in subatomic particles, these are protons. I'm just gonna have that for positive protons. These are neutrons, not carry any electrical charge. And these are electrons. So remember the subatomic particles, which is we are going to look in the next section. So the masses of neutron is similar to the mass of a proton. There is a table here which summarizes the subatomic particles. We'll see later on. However, they do not carry any charge, zero charge for that. Hydrogen, on the other hand, contain one or more proton or neutron. So let's see the subatomic particle, moving on to section 2.6. subatomic particles. These are the subatomic particles, proton, neutrons, and what? And electron. Protons, neutrons, and electrons. I will learn how to represent in this format because it helps me commit to my memory the electrical charge for protons. They are positively charged. For neutrons, they are neutral, they don't have any charge. Electrons, they are negatively charged. Protons and neutrons, as we saw earlier on, have identical masses, and these are the masses 1 AMU, one atomic mass unit, which in grams, this is almost the same as 1.67 times 10 raised to negative 24 grams. It's a small number. If you want to relate to what you know, it's a unit. AMU is atomic mass unit used by chemists and test this numerical value. So you have about 23 zeros before you write 167. It's a very small number. These are the masses of protons and the neutrons. Converting to grams, of course, kilograms. G, the number changes to exponential negative 27. I'll say 1 AMU for neutron, 1 AMU for neutron and protons, but for electrons, they are really small that even doesn't count towards the mass of the atom. Our table 2.1 subatomic particles, showing you the name, masses. I'll rather stick to AMU, 1 AMU, 1 AMU, and 0. You need to know the electrical charges as well. No one will ask you the chi T caret, the chi T caret. So elements on the periodic table, when we say elements, sometimes you get confused and say, what is, is an element, atom? This is the periodic table. On the periodic table here, these are the elements on the periodic table. And when we say they have, all right, they have different number of protons. Remember atomic number 1, 2, 3, 4, from left, right, left, right, left, right. The periodic table is organized in such a way that the atomic number increase from left to right, and the number indicates the number of protons. This is why I want you to understand that the numbers here, you can figure out the number of protons in the nucleus without even knowing the name of the element. For example, here, platinum, number 78, has 78 protons, has 78 protons. I want you to know what is meant by elements or element divided by the atomic number of protons. So the number of protons in the nucleus equals to the number of equals to the atomic number on the periodic table. You'll be given, I'll give you in the exam, I'll give you in quiz if need be, the periodic table. And for now, understand that the number of protons equals to the atomic number of that element. That is what is meant by the number of protons divides the element. Hydrogen has 1 proton, helium has 2 protons, lithium has 3 protons, beryllium, okay, neon, argon number 18, and so forth. You need to learn those names and what those atomic numbers mean. Number of protons in the atom's nucleus is its atomic number and is given Z. So always in this section, C is atomic number, which is what? Position on the periodic table. I was making my raw notes. I wanted to show you this. Let me just minimize here so that you see Z represent atomic number, which is position on what? Position on the periodic table. On the periodic position on the periodic table. So this is an example on helium with 2 protons. It's atomic number 2 on the periodic table. Carbon is number 6. It has 6 protons in the nucleus. The hand here and the pencil, what is this is just the carbon inside the pencil. Helium gas inside the balloon, all right? When here is atomic number represent the position on the periodic table, position on the periodic table. This is a periodic table. You should be able to read. Let me just zoom this. In an exam, maybe you'll just see black and white. But for now, this is to introduce you how to read the periodic table. The number above the chemical symbol is what we call an atomic number, which is represented by Z. And the chemical symbol and beryllium. So if I look at calcium, this is atomic number 20, and it has 20 protons, calcium. Learn the name as early as you can. Here on this slide, I have the periodic table with the names as well as the chemical symbol. You should get started with learning those elements, their position on the periodic table. So each element is identified by a unique number with a unique symbol. So you gotta know what N stand for example, F what stand for. They have the unique, this is nitrogen. And by the way, fluorine is high, the most misspelled element, fluorine. This is R. Should write it correctly. Fluorine. Each element has a unique symbol. I'm using the symbol here. This is helium, this is hydrogen, that is carbon, this is lithium, this is silicon, and so forth. You should learn those chemical symbols on the periodic table. Sometimes it can be 1 letter or 2 letters. For example, carbon, chlorine, and calcium. It can be 2, it can be 1. Chemical symbol for helium, for carbon, for nitrogen. What I want you to learn is the chemical symbol for the first 50 elements. You will need to learn those, and then you will increase. You don't have to learn the same day. You can just split it into just the first 10, the first 10 elements, the first 20 elements, the first 30 elements, and so forth. You may need the index card to learn, memorize, until you commit to your memory the chemical symbols as well as the chemical names. These are just a few given 3 examples. It's not that I will ask you only 3. This is a mistake students make. They think that, oh, right, I went through the PowerPoint slides and I didn't do well in the exam. It's because if you only focus on these 3, it's not going to help you in the exam. All I want you to know is, are you able to learn all these chemical symbols and elements, so that if you are given just without the names, are you in a position to identify the name, given the symbol, or given the symbol, are you able to name? That's where we are going with this exercise, which I want you to learn the chemical symbol and the chemical name. All right, let's see which element contains 50 protons in the nucleus. Of course, it is tin. That is why I say, let's learn, let's get started Given the periodic table, look at the position on the periodic table. Position 50 is for the element thin. All right, Sn. You need to know as well Sn. In case you are wondering why we don't have why Sn not T for thin is because it has some Latin name. For example, sodium, Na. Why not So? All right. Why not So for sodium? It's because it has a Latin name, Nitium, which is Na. Just to give you why this one thing has the chemical symbol Sn. All right. You see 50, show you where 50 is. The 50 Sn is right here. You see element 50 is Sn, not Ti. Ti is titanium. You need to know those chemical symbols and chemical names as well. So right here, correct answer is A. These are just elements that I want you to learn. The position, be able to indicate the number of protons, and remember, protons equals to atomic number. Now, from the Dalton's atomic theory, it's not true that all atoms of the same element are the same. They are not the same. We have what we call isotopes, which are atoms of the same element, but they have different mass number. So here, isotopes are atoms of mass a different number of neutrons. They have same number of protons, but different number of neutrons. Therefore, mass number will be different. So here is the definition. All atoms of a given element have the same number of protons. However, they do not have necessarily have the same number of neutrons. And as a result, the mass number will be different. The mass number will be different. For example, neon Ne for neon, atoms contain 10 protons, but different mass number because of the different number of neutrons. Something may have 10 neutrons, 11 neutrons, or 12. All the three types of neon atom exist, and each has slight difference. We also have carbon-13. Maybe you have heard about carbon-13 and carbon-14. I'll talk about the numbers later on. These are isotopes having different mass number. You should be able to define an isotope or isotopes. Isotopes are basically atoms of the same element with the same number of protons but different number of neutrons. You need to be able to define that, commit to your memory. The relative number of each, the relative amount of each different isotope in nature occurring sample of a given element is probably constant. What that means is the percent in nature of each isotope is relatively constant in nature. The percentages are called natural abundance. That means in nature, we call it natural abundance. We will be using that this time here in a few minutes. All right. So let's see how the sum of the number of neutron protons give us what we call mass number. Remember, C stands for atomic number, A mass number. We call that mass number. And if you look at this, we will come up with what? Sum. So I'll say mass number is given by number of protons plus number of neutrons. This is an equation you need to be able to use in either determining the mass number given the number of protons, or number of protons can be determined by subtracting number of neutrons from the mass number. This is the number A. Don't confuse with Z. Do not confuse with C. We represent isotopes using this notation. Please remember the notation we have, so that for the three isotopes I do have here, this can be written as, or rather, I'll say 12C or 13C or 14C6. In other words, the mass number is the superscript. This is the superscript mass number you see here, the notation mass number. This is the mass number. Atomic number, this is the position on the periodic table. Remember, this is atomic number position in what? On the periodic table, which you see right here. And then the chemical symbol. It could be maybe chlorine 35, 17, and 35. And chlorine 17, 36. And here, this is the mass A equals number of protons number of neutrons. Number of protons, number of neutrons. Here you may be asked to calculate either. This is like a density. If I know 3, this is 1, this is 2, this is 3. If I know 2, I should be able to calculate that one. All right. This is isotopic notation. Here, we call this isotopic notation, and there are 3 of them. All right, isotopic notation, there are 3 ways. Either you are given in this format, or I would say chlorine 35, yeah, this is method 2. I want to say method 2, where you are given the chemical symbol Ivan and a number. These stand for A, which is the mass or mass number, not the atomic number, which is given by protons and neutron, protons and neutrons. We have 3 isotopes of neutron. This is atomic number 10, which is the same as the number of protons. This is the mass number, which is protons plus neutrons, protons plus neutrons. We can also have this. This is a second common notation for isotopes, where we have the chemical symbol Ivan and a number, similar to what I do have there. Okay. Here, just calculating subatomic particles, percent natural abundance for the neon. Neon, we call this neon 20, neon 21, neon 22. Number of protons, number of electrons. If you look at number of protons is constant, but what is changing is the number of neutrons, which will affect the mass number of neutrons, which affect the mass number. An argon isotope has a mass number of 40. So here is mass number, underline the word mass number. I'll say argon. 40, and then 18. How many neutrons? So you remember, number of protons plus number of neutrons equals to the mass number. So if I have here 40 plus neutrons equals to, no, argon is number 18, sorry. 18, so I know it is 18. How do I know it's 18? Argon. If you don't know how to interpret the periodic table, argon is AR, and it's atomic number 18 on the periodic table. Look at this. I don't want you to get confused. Here is the element in question. It is AR argon, and it's position 18. This is what you will do with the periodic table. You will look at the chemical name or chemical symbol, look at this position on the periodic table. Argon is number 18. That's where I got 18 equals to 40, which means N is 40 minus 18. So this is 2. Number of protons equals to 12. No, 22. It's 22. Sorry about that. It's 22. Need to take care of that. So the correct answer is D, 22. From this calculation, look at what I did on my whiteboard. Using this equation, which I'll give you in the exam, to calculate the subatomic particles. Or likewise for phosphorus, you have to know which position it is. And just the way I did before with the periodic table, phosphorus is number 15. Look at it. It is number 15. It has 15 proteins. So if I was to write the isotopic notation for that, it will be P15 and 32. This is the mass equals to 15 plus. So here is 32 equals 15 and equals to 17. You'll do the same thing for the rest. If you look at this, iodine is number 51. So if I was to do that, I'll just write and 131, and here is 53, and 131 minus 53 equals to 78. You have to do the math. So here, please learn the chemical symbol as well as the name. People use the periodic table to determine the position. For example, argon, here is argon is number 18. Tin is number 30. You have to check on the periodic table. Here is SN number 30. It has 30 protons. And then you rewrite that so that you calculate. So here will be zinc 65 and 30. Neutrons equals 65 minus 30. This is 32. 32. Just the way I did the rest, you'll do the same thing for that too. Argon. Conceptual carbon has two naturally occurring isotopes, which image represent carbon-13. It is, you have to count the total number, how many you have in there. The correct answer is A. When neutral atom loses their electrons, they end up being either positive. Yes, they become positive for main group element, losing of electron, they end up being cations. The number of, let's see, for a neutral atom during chemical reaction, atoms can lose or gain an electron to become a charged particle. Yeah, a few examples, positively charged such as sodium are called cations, negatively charged are called anions. How many electrons are present in? This is 10 because oxygen has 8 electrons in total, but the overall charge here indicates that we have extra 2 electrons. So is this going to be 2? If you're wondering how, it's going to be 8 plus 2. This is extra. Extra electrons gives us 10 electrons. Conceptual question for a given element, the size. In light of the nuclear model of an atom, which statement is true? For a given element, the size of isotope with more neutrons is larger. We didn't say that atoms will be large, but the correct answer is for a given element, the size of atom is the same for all of the elements isotope. In other words, carbon-13, carbon-12, carbon-14, they all have the same size. This applies to other atoms as well. This marks the end of part A. I'll come back with part B.